And we march on. We march on into a look at some other very familiar ideas from high school geometry, some of which are true in neutral and some of which aren't. We're going to look at some very familiar things from high school geometry, the idea of parallel lines and transversals and all of that. So let's make sure we remember all of our terms. If I have two lines, not necessarily parallel, and there's a third line that intersects those two lines, that is called a transversal. When the transversal comes through those two lines, you get a whole bunch of angles. The angles in blue are called interior angles. The angles in red are called exterior angles. In particular, alpha and beta are called alternate interior angles, as are gamma and delta. They are alternate interior angles. Alternate because they are on opposite sides of the transversal, interior because they are between the parallel, the two lines in question. They're not necessarily parallel, don't have to be parallel lines to be cut by a transversal. So there's all your vocabulary. It's familiar from high school, two lines cut by a transversal. Here's the thing. That is not what I need. I do not need that. Do I have something else somewhere? No, I don't. That is just terrible. Okay, so we'll skip to here. This is the alternate interior angles theorem, and it says if L and L prime are two lines cut by a transversal T such that alternate interior angles are congruent, then L is parallel to L prime. We did this in high school. If you see congruent alternate interior angles, that means the lines are parallel. Here's the way this works. You've got L, you've got L prime, you've got a transversal, and alternate interior angles are congruent. Doesn't matter which pair, either pair will be fine, so we'll pick this pair. Why do the lines have to be parallel? Well, what if they crossed somewhere way out here? Maybe they cross way out here. Then, for this triangle, that is an exterior angle. And that exterior angle would be equal in measure to this interior angle, and that is all sorts of bad. Doesn't matter if they cross on this side, or if we were to extend the picture to the left and they cross on that side, it does not matter. You get an exterior angle that's just as big as an interior angle of a triangle, and that is bad. So the lines are not allowed to touch. I will issue the following warning. The warning goes like this. The logic only goes one way. If alternate interior angles are congruent, then the lines are parallel. It is not necessarily true that if the lines are parallel, then alternate interior angles are congruent. You've got to get the logic straight on that, because the one way is neutral and the other way isn't. Well, once you have alternate interior angles, you could go at it a different way. You can talk about two lines, L and L prime, cut by a transversal such that corresponding angles are congruent. If corresponding angles are congruent, are the lines parallel? And I think you'll figure that out quickly enough. I will prove this when we get into class. Of course, you've got the same side interior angles. The same side interior angle theorem goes something like this. If I have alpha and beta, if alpha plus beta is 180 degrees, then L is parallel to L prime. And that won't be very hard, and you will pick up on that when we get into class. Now, these are all things that you can pick up in a standard high school geometry class, except that we are proving them in neutral geometry, which does not depend on the Euclidean parallel postulate. There is a corollary. It is a huge corollary, and so I will share it with you. The corollary goes like this. It's not called the huge corollary. I'm using huge as an adjective. It's not the name of the corollary. If L is a line and P is some point not on L, then there exists some line M parallel to L through P. If I have a line L and some point P, I can draw a parallel to L through P. And you say, wait a second, that's not neutral. Yes, it is. It is an existence theorem. It says there exists at least one. There could be more than one, as is the case in the hyperbolic parallel postulate geometry, that hyperbolic geometry has more than one. There exists one. This is where the elliptic parallel postulate is just going to drop off the face of the earth for us. This is the reason. So it's not too hard to prove. You just drop the perpendicular from P. That perpendicular has some foot down here, perpendicular. And then you say, wait a second, that means I can drop a perpendicular to this transversal through P. And once I have that, I have a pair of alternate interior angles that are congruent, and therefore line M has to be parallel to line L. And we're going to do this fairly frequently where we do the double perpendicular construction to get ourselves a parallel line. This corollary has huge meaning. Obviously, it means that the elliptic parallel postulate is false in neutral geometry. You cannot have a neutral geometry that takes the elliptic parallel postulate. It also means if two lines are perpendicular to the same line, they are either the same line or they are parallel. And that is familiar to you from high school. Okay, so there you have it. That's our lesson on transversals and parallels.